Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for MTech EC first semester students. Myself, Dr. Surajit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata, and this is my official email address. Today we are going to start lecture number 5 from the module that is baseband signal receiver and probabilities of bit error. Actually, in the last class we have started BPSK modulation scheme. We have draw the constellation diagram and find out its error probabilities. Now today our topic is generation detection and bandwidth requirement in BPSK. And the lesson objective of this topic is analyze signal vector representation of various digitally modulated signals by creating signal constellation and compute the bit error performance. And this topic is mapped with CO number 2. So let us start lecture number 5 from the module of baseband signal receiver and probabilities of bit error. So first is the generation of BPSK signal. And figure number A, first figure is the generation of the BPSK signal and second figure is the detection, coherent binary detection of BPSK signal. Now, in equation, we already see that to generate a binary PSK signal, we have to represent the input binary sequence in polar form with 1 and 0 represented by constant amplitude levels of plus root over EB and minus root over EV respectively. The signal transmission encoding is performed by a polar non-return to zero level encoder. The resulting binary wave and a sinusoidal carrier phi 1t whose frequency fc or phi 1t equal to square root of 2 by tb cos 2 pi fct is applied in a product modulator and ultimately we get the binary PSK signal. Now to detect the original binary sequence of 1 and 0s, we apply the noisy PSK signal XT, that is at the channel output, to a correlator circuit, which is also supplied with a locally generated coherence reference signal phi 1t. The correlator output X1 is compared with a threshold of 0 volt in the decision device. If X1 greater than 0, the receiver decides in favor of symbol 1. On the other hand, if X1 less than 0, it decides in favor of symbol 0. If x1 is exactly 0, the receiver makes a random guess in favor of 0 and 1. So this is all about the generation and detection techniques of BPSK signal. Next is the power spectra of binary PSK signal. From the modulator in first figure, that is the generation technique figure A, 6.4a, we see that the complex envelope of a binary PSK wave consists of an in-phase component only. Furthermore, depending on whether we have symbol 1 or symbol 0 at the modulator input during the signaling interval, say t equal to 0 to TB, we find that this in-phase component equals plus GT or minus GT respectively, where GT is the symbol shaping function and which is defined as GT equal to square root of 2EB by TB whenever T belongs to 0 to TB. Otherwise, it is 0. Now, we assume that the binary input wave is random with symbols 1 and 0 equally likely, and the symbols transmitted during the different time slots being statistically independent. Therefore, the power spectral density of a random binary wave is equal to the energy spectral density of the symbol shaping function divided by the symbol duration. The energy spectral density of a Fourier transformable signal GT is defined as the squared magnitude of the signal's Fourier transform. Hence, the baseband power spectral density of a binary PSK signal equals SBF, defined as SBF equal to 2EB sin square pi TBF by pi TBF whole square, which is 2EB sin square into TB into F. So this power spectrum falls as the inverse square of frequency, which is shown in this figure. So this is the spectrum, and where it is a normalized frequency FTB and it is a normalized PSD SBF by 2 TeB. So the maximum amplitude is 1 and this is the spectra. Primary lobe is cut at 1 and secondary lobe is cut at 2. So I now solve. This is all about BPSK signal. Now some problem is solved, and this type of problem is very much usually comes in the semester as well as GATE examination. So the first problem is very interesting problem. The signal component of a coherent PSK system is defined by ST equal to AC K sine 2 pi FCT plus minus AC into square root of 1 minus K square into cos 2 pi FCT, where T belongs to 0 to TB. And the plus sign corresponds to symbol 1 and the minus sign corresponds to symbol 0. The first term represents a carrier component included for the purpose of synchronizing the receiver to the transmitter. Now draw a signal space diagram for the scheme described here. And second, the show that in presence of additive white Gaussian noise of zero mean and power spectral density in 0 by 2, and the average probability of error is P equal to half ERFC square root of EB by N0 into 1 minus K square, where EB equal to half into AC square into TB. Clear? So this is the expression of coherent PSK system. First, draw its signal constellation diagram, signal space diagram. And here the plus sign represents 1 and minus sign represents symbol 0. And second, you have to calculate the average probability of error. So first draw the signal space diagram. See, there are two parts in phase, that is cosine part and other is sine part. One is cos term, another is sine term. So there are in phase and quadrature, both components are present. So this is the sine part, quadrature component, the sine part, and symbol 1 and symbol 0, that is plus AC TB by 2 1 minus K square and minus AC square root of TB by 2 1 minus A square, and the sine part, that is AC K into square root of TB by 2. So quadrature sine part and cos part, one is plus 1 for another is minus 1. So the signal space diagram differs from the conventional PSK signaling scheme in that it is two-dimensional with a new signal point on the quadrature axis at ACK into square root of TB by 2. Okay. And second is the, you have to calculate the average probability of symbol error. So first is signal is coming ST plus WT, and which is for coherent BPSK system, and it is multiplied with cos 2 pi FCT. Then it goes to the integrator circuit, and after, suppose the output of the integrator is L, and then this goes to a decision device for a decision theta, and H1 and H2 is the output. So the signal at the decision device L, which is say ST, your ST is now becomes like that, this expression. So ST plus WT multiplied with cos 2 pi FCT. Just this, if we multiply it and with cos 2 pi FCT, this part is for noise, that is for WT cos 2 pi FCT integrate 0 to TB dt. And for the first term, that is first term is the sine 2 theta, sine 2 pi FCT cos 2 pi FCT. So 2 sine A cos B sine 2 theta, and this term is 0. And cos square theta half into 1 plus cos theta 2 theta. So only DC term is present here. So now it now becomes plus minus AC by 2 square root of 1 minus K square TB, and plus this term is the noise term. So therefore, following a procedure similar to that used for evaluating the average probability of error for a conventional PSK system, we find for this system the average probability of error is PE equal to half ERFC into square root of EB into 1 minus k square by N0, where EB equal to half AC square into TB. So in this way you can solve this type of problem. Now I am showing you another problem. This is also very much interesting. Consider a phase locked loop consisting of a multiplier, loop filter and voltage control oscillator VCO. Let the signal applied to the multiplier input be a PSK signal, which is ST equal to AC cos 2 pi FCT plus KP into MT, where KP is the phase sensitivity and the data signal MT takes on the value +1 for binary symbol 1 and -1 for binary symbol 0. So the VCO output is like that, RT equal to AC sine 2 pi FCT plus theta t. Now evaluate the loop filter output, and assuming that this filter removes only modulated components with carrier frequency 2fc. So how to solve the problem? Just actually it is a PLL VCO, and at the input of the loop filter we apply basically a PSK signal. So the noiseless PSK signal is given by ST equal to AC cos 2 pi FCT plus KP into MT. So just using trigonometry formula, cos A plus B, cos A cos B minus sin A sin B. Now you know that sin MT equal to, since MT equal to plus minus 1, because it follows, so it follows that cos Kp into MT equal to cos plus minus Kp. This part. So cos of minus theta, that means actually cos theta, and sin of minus theta, that means minus sin theta. So now it becomes plus minus sin Kp, or now it becomes MT sin Kp. Therefore ST equal to just AC cos Kp cos 2 pi FCT minus AC into MT sin Kp into sin 2 pi FCT. And now the VCO output is already given, that is RT equal to AV into sin 2 pi FCT plus theta t. So the multiplier output is therefore just simply multiplication RT into ST. Just simply multiplication RT into this expression ST. And ultimately we get this expression, just simple multiplication. So the loop filter removes the double frequency component and producing the output ET equal to half AC AV cos Kp sin theta t minus half AC AV MT sin Kp into cos theta t. Now note that Kp equal to pi by 2. That is, the carrier is fully deviated. There would be no carrier component for the PLL to track. Okay. So this type of problem comes in your examination or in GATE examination. So this is all about BPSK. Okay. So let us stop here. Thank you. And in the next class, we start from QPSK system.